So now we move to our final of the three main notebooks, and this is called the Wikipedia Affiliated Actions. So let's bring that up. And we're starting from this user or contributor username, just shorthand for user, having some relationship to a log title. So this is kind of the basic graph we've been working with. Now we want to take this beyond this initial point and begin to introduce some affiliated connections between users based upon shared activities on a page. So as we get into this, we're going to load in the edge and vertices data frames that we had just saved off in the previous notebook. And we now have those available to us to create a graph frame over. We're going to cache the vertices because the graph vertex is used a lot as we create various subgraphs. So we want to actually have that on the cluster. We don't have to, but it gives us a little bit of a speed up. And again, we can see the schema if we wanted to verify what that was. So we're going to start out with some motif finding. First, what we want to actually affiliate is only users who have a flag. So they have to have a flag, any flag, in order to be a participant in this affiliation graph. And this would be a representation, the gray edges would be a representation of what we already have, users connected to log titles. But what we want to add to that is now users connected to users because they've both made an edit on a common page. And this can't be a user. User can't be affiliated with another user because of this action that involves another user. So we're not going to do that. We're going to keep it to pages and talk, essentially. Or I should say not user. As long as it's not user, we'll allow it. So that's where we're going. First, we want to figure out the paths that are flags. So to do that, we use motif finding. We do a simple triplet definition here of a source by relationship to a destination, and they must have greater than 0 flags. And we get back information which we could explore if we wanted. And that's what we're going to be using to continue on to build the affiliation graph. So we want to actually get a subgraph back off of those paths because those gave us paths, but we actually want to get back to a graph. So to do that, we're going to select back out from those paths something that would be able to be created back as a graph. So we're going to use the full out vertices that we had on our graph where we started from. That's all vertices available. That's not going to change throughout this. That master set won't change. And then we're going to just select out of the flag paths all the key information on the edges to basically build back an edge data frame, build a graph around that, and then we have this nice function that allows us to drop isolated vertices, which means only include vertices that actually have an edge. So there we are, and from that graph we actually want to do motif finding again to get to this affiliation that we're talking about. And so the pattern we're looking at is an entity A connected to a entity B that is a page or talk or essentially not a user. And then we want to figure out another user that's connected to that same page. Okay, and so we'll have these this chain of fields, essentially nested fields, when we run our pattern. So we take the output of the paths we just found to identify the A to essentially C that we're going to be interested in, and we have 15,000 paths. Okay, so now we want to actually generate the subgraph that will allow us to get this A to C and C to A bidirectional relationships. And when we do that, we're going to add the unique shared properties or properties of the transaction or log item between A and B, which comes between A to B to C. So we're going to actually maintain the properties that were for A to B because that's the transaction that they share, and coming steps to generate back a edge direction 1, which is essentially A to C, and then we generate a C to A direction here. And then ultimately we create the edges combined by taking the edge direction 1, unioning that with edge direction 2, and we do some drop duplicates just to make sure that we don't have any surprises there. And we now have the affiliated with flags edges. And so here we're going to union our edges back with our master graph, because we don't just want affiliated edges, because that loses information. So we want to union our affiliated edges back with the base graph to now have one even bigger sort of set of edges than we started with. So we have that now with these union edges, and we can build an augmented graph frame using what we just described. So we can go further from that. We can do the out degrees. We can figure out which users are the most highly connected. So just using the graph frames algorithms, we use out degrees, and we can see, that Oshawa is the most active with 9,000 plus activities, and then so on. And these are probably, when you get into certain levels of activity, these are probably curators of some sort at Wikipedia, which over time we could get more familiar with and understand sort of, without even seeing an org chart or a who does what, we could actually understand roles by graphing and analyzing the types of contributions that different users make. So we explore Oshawa a little bit, and we look at Vandal flags that he essentially has been the source of flagging. And so we can see various users that he's actually blocked, and we could explore any of those users to maybe learn more about them. So that's what's happening here. And then we can look more broadly than that one user, Oshawa, and we can look at what are the total blocking actions. And to do that, we can just basically do a sum of hard flags, soft flags, group them, and then sum them up to get counts for each. And we see that we have, some 3,000 hard flags and only a handful of soft flags among blocked actions. So most block actions are because of more serious offenses than a soft action. And we can take a sampling if we want to know how many blocked users were actually flagged as vandals. We can basically do that a couple of ways. We can do a sample and then do some built-in aggregate functions here in Databricks. I'll just pull that up briefly. We're doing an aggregate inline here to count and understand and get an estimate. And that shows up as 8% blocking. We can check our math on that just by doing the rigor of actually calculating it without taking a sample, and the actual number is 8.14. So our estimate wasn't very much off at all. So we go further from there. Connected components is something that might help us in this case. Now we have brought in these affiliated layer to our graph, so we have a lot of interconnectivity due to anyone that shares a flag and shares a page has a link. So we continue on with the connected components. We decide that it's best to drop the new users. That really doesn't get us anything, and it's actually a large number of actions are just new users coming into Wikipedia. So we drop that edit type to help free up kind of wasted edges that won't get us anywhere. And that reduces us down to some 400,000 edges and some 500,000 edges, some 400,000 vertices. So we build our CCG, our connected components graph, by joining back the component ID to the augmented graph. So this is kind of our most complete graph that we'll work with going forward. So we have kind of the extent of everything we're going to do from a analytic to build the graph. We now have it, and because we have it, we're going to cache the vertices and the edges on CCG. The size is not so big that we can't do that, so we cache it, bring it in, and we can begin to do more analytics. We can understand you know, how many of the connected components have edges involved in vandalism. And that is, again, a sharp tail, but it's a lot smaller than the 300,000+ that we saw of all edges earlier being involved in component 1. We only have 5,000 now that are involved in vandalism, so that's actually getting to be pretty manageable. And then it tails off very sharply to 3 and then to 1 in terms of the rest of the component IDs. So we know that our affiliation graph that we just built is contributing heavily to this characteristic of component 1. So we could do a little more on components, but I think that's probably plenty for that. Now we change gears to look at a particular user. This section is driven by the widgets here at the top. So we have a vertex ID that we could put in. We're starting with this nefarious character. I won't try to pronounce his name, but we have that individual. And then we have the ability to restrict that by begin day and end day. To drive, you know, the results that we ultimately want to visualize as well. So there's some information on this blocked user. So we know he was blocked due to vandalism and other activities. We can look at him from any relationship or edge that he's involved in, either as the source or the dest, and we can actually order his those edges by day within the month of October in this case, to understand how active he's been or actions taken against him. So we could learn a lot if we wanted to or needed to about his activities and activities around him. We could also figure out what artifacts he created. So we could go through and filter by edit type of create to understand that, you know, he created a number of different pages and templates, talk pages, things of that nature. And for each one of those, you know, you could go and look and see what the effects were of his changes if you wanted to go that route. And we can also understand just the edit types. So we can basically say, you know, what are the edit types that are out there, just to help kind of know in rank order what is the most common. So create is a very common type of edit or action that is taken in the system. So going through this can be helpful just to understand what is more common and less common types of activities. So now we want to actually visualize the activities of this blocked user. Okay, so we come back after looking at HoloView's helper. And now we want to look at doing a 2-hop affiliation graph for whatever's in the Viz Vertex field. And this will respond if we were to make changes here. It would be able to respond and refresh the output. This code could be hidden, but we're showing it just to understand what's happening to users and understand who's who. So this is the main user who is blocked. Let me actually scroll down a little bit. So this is the main user here who is blocked, and we could actually pin him and begin to look around at users that he is connected to if we wanted. There's a couple of different ways to get at this. So this is using HoloViews and then some, you know, basically some customization around the edge sizes, basically how wide they are and the size of the nodes and the color of the nodes, but this is really pretty much out of the box in terms of what we're using. So we could also look at more from this information. We could actually look at information more in a tabular fashion, or take actions to do other analytics against the data resulting from the filtering we did above. So we could look at the just the edges with where the blocked user or the user of interest is the source, and we could also see all edges regardless of whether the user of interest is the source or not. So that concludes the bulk of the work. There's always more nuance, but hopefully this gives you a good sense of what we've done, and hopefully the other materials that are submitted will further augment and bring understanding of the type of activities done in this demonstration. And I hope you enjoyed watching it.